Hello, everybody. So welcome to lecture 13 on this fine Thursday, where we are going to continue from where we left off of lecture 12, talking about moment magnification and slenderness effects on column design. So before we get started, picking up where we left off last time, does anybody have any questions you'd like to ask of me of homework or lecture? Okay, so somebody asked me an interesting question during an office hour about homework number 7, which I realize you may or may not have taken a look at yet, but it's an interesting question, and I wanted to share that with the class. So let me do this. If this is your column in plan view, and here's a rebar, here's another rebar, and another rebar. And we look at it from the side and we draw a side view. So there's the surface. And if I draw the strain condition to be something similar to what the homework has a strain condition that looks like this. Okay. And as always, the failure strain of concrete is assumed to be 0.003. So that's the strain over here on the far compression side. And the homework assigned that the strain over on this side is 0.001. It's still in compression, okay? So the strain in the steel, which is located here, you have to find that strain by using similar triangles. And the strain in this steel, here, you can find that strain by using similar triangles. And once you have the strain in these two rows of steel, then you can figure out what the stress is. If the strain is less than the yielding strain, then you use Hooke's law. If the strain is greater than the yielding strain, then the stress is 60 KSI. Super simple. But here's where the question I think gets interesting. Where do you measure little c? How do you measure little c? Well, little c is defined as the distance from the neutral axis to the point of maximum compression. Well, where does the strain equal 0? Where's the neutral axis? Well, that point is going to be out here someplace where the strain is equal to 0. So the strain is going to equal 0 actually someplace outside of the section of the column. Is that disturbing? Is that bad? No, not at all. It's just a measure of where the strain is equal to 0. So this distance from here to here, that distance is little c. Okay, does that make sense? Is there anybody there?
So it has to be more than 24.
In this case, little c will be more than 24. That's right. So sometimes I think that might trip up people because it's outside of the column. But that's okay because it's just a projection of the strain. If the column was much, much wider, this would be where the strain is equal to 0. Well, the strain, it still would be equal to 0 at a distance c, but c is going to be greater than 24 inches. Okay, and that's perfectly fine. It's just a measure of where we go from 003 to 0 strain is little c. And it's okay if it's outside of the column itself. Little c can be greater than 24 inches in this case, if the column's 24 inches wide. But then here comes the next question. Where is little a? Where is the width of the compression block? Okay, so to do that, we say A is equal to beta 1 times C, right? And it is. But if little a ends up being out here someplace, if that's little a, well then that can't be little a. You can't have a compression block bigger than the actual physical concrete. So if that were the case, then your compression block would just be the entire column, like it is for pure compression. Your compression block for pure compression is the whole column. So if A equal to beta 1 times C is greater than 24 inches, then A is equal to 24 inches. It can't be bigger than the actual available concrete. But if little a is less than 24 inches, then little a is whatever little a is. And that's totally fine. Even if C is bigger than the section, little a, if it fits in the section, then that's what it is. If little a is actually bigger than the section, then you make it the size of the section. Okay? Does that make sense to you guys?
Is that, professor, in like in the specification,
Is that
or
it? I'm sorry, is that in what?
the like when you're saying that if A is greater than the width,
Yeah.
and so we need to use like what's the actual width, but if it's less than, then we use the A. Is that in the code?
Kinda, sorta. Not really. Kinda, sorta.
So this is like a special case, right?
Well, I'm just kind of filling in the blank, if you will.
Uh-huh.
It is in the code because let me say it this way. What if this is your column, and I'll draw it up here this time, okay? And what if your column was the pure compression case? So the pure compression case, then the strain is the same all the way across, right? As we talked about before. So with the pure compression case, the strain over here is 0.003. The strain on this side is also 0.003. It's 0.003 all the way across, okay? So in this condition, what is the value of C? What does C equal? If the strain is 0.003 here, and the strain is 0.003 here, then if I stretch this off to the side, how far is little c?
It's infinite.
Thank you. It is infinite. That's absolutely right. So let's say this was 0.029999999 instead of 0.003. Just the teeniest micron less on this side. Then C would be a real number. It might be 6 miles, but it would still be a real number. It's a calculable number of inches to where C, where the strain diagram crosses the neutral axis. So say that C is something really big, and I'll just draw it exaggerated, kind of like out like this. Okay. Remember, we're talking about the pure compression case. Then beta 1 times C, if C is equal to 1,000,000 inches, then what's beta 1 times C? Something like 850,000 inches, okay? Well, that's ridiculous. You're not going to have compression over 850,000 inches. You're going to have compression just over the section of the column, which is what we did for P naught and Pn and PhPn. Those are just assuming that the whole section of concrete is evenly and equally in compression. But what we're really saying is C is nearly infinite. So little a is nearly infinite. But because A is bigger than the available concrete, then we use A as the area of concrete. So this is the same thing. I'm doing exactly the same thing. It's just that C is not nearly infinite or millions of inches. C is a real number that you can calculate. It's not that big of a number. It's just bigger than the column itself. So this is how you treat little a. Again, if little a is bigger than the available concrete, then you just use the available concrete. If little a is less than the available concrete width, then it's like everything else you've done. You just use a as you calculate it. Okie dokie. Any questions on that concept? Okay. Hopefully that was enough of an explanation so that when you hit your homework this weekend, you won't freak out and you'll know what you're looking at. Okay. Few people have joined us since the last time I asked. So before we dive into part 2 of this lecture, does anybody else have any questions they would like to ask? Homework, lecture, anything? All right. So let's get started. Where we left off last time is we calculated 5 points, point A, B, C, D, and E. We constructed this interaction diagram for a frame column that we had defined. And now that we have our capacity interaction diagram, now what we need to do is calculate what the demand is, what the loads are to go into this interaction diagram. We start by calculating the effective length of the column. And we find psi A at the top of the column. Psi A, if you remember, is the summation of the stiffnesses of all the columns coming to a joint divided by the sum of the stiffnesses of all the beams coming to a joint. I put this in here as a refresher. This is our problem statement from last lecture. So if you remember, we're talking about, it's basically a bent frame with a pin support at the bottom and at the top. So this is joint A and this is joint B. At the top, we have one column framing into that joint and we have one beam framing into this joint. The example problem, example number 3, also to refresh your memory, is a braced frame. So this frame is leaning on something else to give it lateral support or stability. And we're just trying to analyze if this column has slenderness effects, if this column has a tendency to buckle, we're analyzing how much to amplify the applied moments to make sure that we're still safe, even with these tendencies of slenderness. Okay, so this, just a refresher, this is what we're talking about. And this column has 8 number 7s, all 4 of them on each side face in this direction. And this is a section of the beam. Okay, so we need to find psi A and psi B so that we can calculate our K factor. The modulus of elasticity is 57,000 times the square root of 4,000 was our F prime C, so that's 3605 KSI. The moment of inertia is BH cubed over 12, but we're using 70% because it's a column. That gives us 9,333 inches to the fourth. The column height from top of footing to the center of the joint is 26 feet or 312 inches. The moment of inertia of the beam is BH cubed over 12 as well, but we only use 35% for the beam. So that gives me 27,216 inches to the fourth. And the center joint to center joint length of the beam is 27 feet or 324 inches. Assume the columns and beams are all poured with the same concrete. So the modulus is the same for both the columns and the beams. And now I can go into my equation for psi. I have E times I over L for the column, E times I over L for the beam. I get 0.356. Psi B at the bottom of the column at the footing, because it's a pin connection, we're going to use 10. We're just, for a pin connection, we just use 10. Theoretically, at a pin connection, psi is actually infinite, but we like to use practical numbers instead of infinity, so we're going to use 10. Also to account for that, there is no such thing as a perfectly pinned connection. And as you can see from the interaction diagram, see where the 10 is up here, and then there's 50, and then there's an infinity. So it's not even logarithmic. It just jumps exponentially. So there's not a huge difference here between 10 and infinity. So that's why it's just a good choice. Okay, so now I plot out. Psi A was 0.38 or 0.36, and psi B is 10. So I plot it out here. And what I get is 0.78 from the alignment chart. Okay, so I'm going to figure out my radius of gyration. I'm going to use the 0.3 times h. So 0.3 times 20 is 6 inches. And so my KL over R ratio, that was the whole point of using the alignment chart, was to get K. So I have 0.78 times unbraced length of 312 inches over R is 6 inches, and I get 40.6. So my KL over R ratio is 40.6. I compare that to my allowable. I gave this in the last lecture. The allowable is 34 minus M1 over M2. And M1 in this case, it was a pin connection at the base, so M1 is 0. M2 was given as 80. So 40.6 is greater than 34. Therefore, I must consider slenderness. Also, 40.6 is greater than 40. That was that other criteria. So I calculate my Euler's critical buckling load as pi squared times EI effective over KL squared, where EI effective is defined by ACI 318, section 66444, as either A or B or C. We get to choose A, B, or C. A is 0.4 ECIG over 1 plus beta DNS. NS stands for non-sway. Or 0.2 ECIG plus ESISE over 1 plus beta DNS. Or ECI over 1 plus beta DNS. And this one is deceptive. That one looks like, oh, that's the easiest one. But that I is more complicated. Okay, so for this example, we're going to choose option B. And now we need to calculate these components. So I gross of the column is BH cubed over 12, or 20 times 20 to the third over 12, is 13,333 inches to the fourth. ISE is the moment of inertia of the pattern of steel. So what we're going to do here is, remember, when we calculate the moment of inertia due to steel, we neglect the term of the moment of inertia of steel about its own axis, because a circle about its own axis is an insignificant moment of inertia. But what is not insignificant is the polar axis theorem. So we take the area of the steel times the distance of the steel to the centroid of the column. So half of the width of the column is 10 inches, and the steel is located at 2.5 inches off the face. So the distance from the center of the steel to the center of the column is 10 minus 2.5. And if I go back here a little bit, to here, you can see that these four all have the same distance to the centroid, 10 minus 2.5. And these four all have the same distance to the centroid, 10 minus 2.5. So that's why I could do all 8 of them at the same eccentricity. Okay, so I got 8 number 7s times 7.5 inches squared is 270 inches to the fourth. My B, D, and S is the ratio of the sustained load to the total load. And the problem statement specified that 550 kips of the 800 was sustained. So that's 0.69. So now I can calc it out. I plug in 0.2 modulus for the concrete, moment of inertia of the concrete, modulus of the steel, moment of inertia of the steel, over 1 plus beta DNS. And this is 10,321,400 kip inch squared. So now I can plug it into my critical buckling load, where this is pi squared, my 10 million here. My K was a 0.78 factor, and my unbraced length LU was 312 inches squared. And this calcs out to 1,677 kips. CM factor is 0.6 minus 0.4 M1 over M2. M1 is equal to 0. M2 is 80. So KCM equals 0.6. So now in my delta equation, I can plug in my CM of 0.6, my applied axial load 800 kips, and 0.75 times my Euler's buckling load, and I get 1.65. So delta is equal to 1.65. My minimum moment needs to be checked here. I have an applied moment of 80 kip feet, but there's a minimum that we have to check against, and that is the axial load times 0.6 plus 0.03 times h. This is in inches. So 800 kips times 0.6 plus 0.03 times 20 is exactly 80 kip feet. So it's the same. The applied moment and the minimum moment in this case were the same. If this number was bigger than 80, then we would use our minimum moment. So my MC, it's my applied load, is delta times the actual load. So I'm amplifying the actual load to account for the buckling condition. And so 1.65 times 80 is 132 kit feet. This is my amplified load. And when I plot 800 and 132, it still falls inside of my interaction equation. So by mechanics of material, it works. It's still within the capability or capacity of the column. The factor load coordinate with amplified moment is still within the interaction diagram. But, and I hate this provision as much as anybody, it is so troublesome. But there's an ACI 318 section 626 that says delta cannot exceed 1.4. We have a delta 1.65, so this column would need to be redesigned to reduce delta. Okay, how could I do that? Where were some of my options? How could I reduce that delta? Well, this is my equation for delta. What can I change in this equation? Can I change the CM factor? No, I can't change the CM factor because it's a function of the applied load. And I'm assuming I have no control over how much load this thing's supposed to take. Can I change the 800 kips? No, because that's the applied load as well. The only thing that I can manipulate is Euler's buckling load or Euler's critical load, P sub C. So what is in P sub C? P sub C has pi, can't change that, EI effective, K, and LU. Well, possibly I could change K or LU by changing the geometry of the frame, but most likely not. That's the frame they want. So really the only thing I can change is EI effective. So my equation for EI effective is here. So what can I do? What can I change to reduce delta? Really, all you can change is E or I. E is a function of the modulus of elasticity of the concrete. So you can only change that by increasing your strength of concrete. So I could go from 4,000 PSI to 5,000 or 6,000 PSI, and that would increase the modulus. That would help. What else could I do? I could increase my steel. Increasing my steel also as a contribution to this, that would make this stiffer. And I could change my I gross. I could actually make the column bigger. So instead of a 20 by 20 column, try a 22 by 22 or 24 by 24 column. And that would actually help quite a bit in making this stiffer. The stiffer you make the column, then the higher your Euler buckling load goes. And the higher your Euler buckling load goes, that's in the denominator. So the higher your Euler buckling load goes, then the lower delta goes. Okay? So that's really the only options you have as a designer, is to either increase the strength of the concrete or increase the size of the concrete or add more steel to it, and the steel would also stiffen the concrete. One other thing though you could look at before we move on, remember we chose option B to calculate the effective EI stiffness of the concrete column. You could investigate using option A. That might work better, not sure. Or you look at option C. So if option A or option C gives you a better number than 10.3 million, then that's free because you don't have to change anything about the concrete frame. It just works because you're choosing to use a more accurate assessment of the actual stiffness. Okay. So that, as a designer, that might be the first place I go, is try one of these other equations and just suffer through the complexity of the equation to get a better number. If it still doesn't work, then I got to start changing material properties until I get it to work. Oh. Okay, so that was our example for non-sway or braced columns. Any questions?
So is it always that delta cannot exceed 1.4?
Yes, it is. I looked and searched and scoured for the loophole. There's no loophole. And it wasn't always like that. It was just the last couple of code cycles that they added in that 1.4 factor. But there's no loophole. There's no out. So yeah, you're pretty much stuck.
And then you say if, let's say, our delta is greater than 1.4, but if we use, let's say, option A or C, and then the delta is less, is that still like okay?
Yes, it is. Yes, it is. It is. Doesn't matter that you tried B first and it didn't work, then you try C and it does work. Because remember, what you're doing by going from B to C is presumptively you're using a more accurate assessment. It's not as conservative, it's supposed to be more accurate. So you can, if the more accurate answer works, then you're always okay using the more accurate answer.
Okay.
And that's kind of a strategy a lot of structural engineers will do, is they'll use the easy answer first, the one that's quick and dirty and easy. And if it works, great, because they know the more accurate one's going to work if the cheap and dirty one worked. But if the cheap and dirty one doesn't work, oh man, all right. And then it'll go back and, spend time and crank out the more complicated answer, hoping that it gets them to the solution that works. If the most complicated version of the solution still doesn't work, then you have to kind of just step back and go, you know what? It doesn't work. If it doesn't work, it doesn't work. I got to change something.
Okay. That makes sense.
Okay. Any other questions? All right, so we're going to do the same thing, only now what we're going to do is we're going to look at the moment magnifications delta factor for a sway or unbraced column, as opposed to the one we just did was a braced column. And you'll see what the differences are. Okay, so for sway columns, ACI 318-66461, the factor design moment, and this gets a little more complicated. M1, remember M1 is the lesser of the two end moments, M1 and M2. So M1 is equal to M1NS. This is the moment due to non-lateral loads. And this is already a factored moment. Plus delta S. Delta S is going to be that moment magnification factor times M1S. And M1S is the portion of the moment that is due to lateral loads. So what they're saying basically is all your factored loads, some of them come from gravity load that doesn't cause it to sway laterally. And some of the load comes from lateral loads that does try to knock the building over sideways. We're only amplifying those moments that come from the lateral loads, not from the ones from gravity loads. So that's why we split it into two parts. And then M2, same idea, is equal to the moments due to non-sway plus delta S times the moments due to sway, where M1 is the lesser, M2 is the larger of each end moment. ACI 318-66462 gives the moment magnification factor as one of A, B, or C. If delta S is greater than 1.5, so it can be greater than 1.4 as opposed to brace columns, but if it's greater than 1.5, then only B or C are allowed. A is this delta S is equal to 1 over 1 minus Q greater than equal to 1, where Q is equal to the sum of the factored axial loads of the whole story. So this would be like if you have 20 columns on the ground floor, it would be the sum of all the axial load on all 20 columns on the ground floor. Times delta naught. Delta naught is the deflection due to the lateral loads. VUS is the VU, that's the factored shear for that whole story. So it's not per column anymore, it's for the whole story. And then LC is the unbraced length of that story. Or B, delta S, and this is like the same as the brace condition. Delta S is equal to 1 over 1 minus sigma PU over 0.75 times sigma PC. So it looks a lot like the Euler buckling load equation. But for sway columns, it's the sum of all the axial loads divided by the sum of all of the Euler critical buckling loads for that story. Why? Why do we keep adding up everything for the whole story? Well, if you picture a building, and again, it has 20 columns on the ground floor. If one of those columns is going to buckle by swaying out of plane, it has to take all the other columns with it. You can't separate one column from the other 19 columns because they're all tied together with a concrete floor. So it's if it's going to have a buckling or slenderness problem, the whole floor is going to buckle over, not just a single column. ACI 318, section 66462, where sigma PU is a summation of all the factored vertical loads in a story, and sigma PC is the summation for all sway resisting columns in a story. PC is calculated using equation 66442, with K determined for sway members from 66443 and EI effective from 66444 or 66445 as appropriate, with beta ds substituted for beta dns. And I will walk through an example because I know these are kind of obscure code references. Or C is, instead of using some simple equation to derive a factor, you can always just build the whole thing in a sophisticated finite element or frame program and run a second order analysis. You can always do that. But that requires modeling and it requires software. So a lot of engineers don't want to do this when you can just do this and do it on pencil and paper. ACI section 66464 still dictates the use of the C sub M factor per ACI 318-6645. M1 and M over M2 is negative if the column is bent in single curvature, positive if the column is bent in double curvature. Per the textbook, this CM factor, this is the author's interpretation. This C sub M factor should only be used if a maximum moment occurs somewhere other than one end or the other. For all other cases, take C sub N equal to 1.0. Okay, so let's get to example number 4. We have 4,000 PSI concrete, 60 KSI steel, and here's a very similar frame to the one we just did. Very similar. Same footing, same column section, same beam section, same geometry of the frame. Difference is I don't have pins here anymore. Why? Why don't I have pins? Because this has a lateral load pushing on it, and it wouldn't have enough strength to resist that lateral load. It would buckle over. So I had to fix the column to the foundation, and it's clearly fixed at the beam here. And then the loading is totally different. I have this distributed load across the beam. I have factored axial loads at each of the columns, and I have a shear load that is tending to bend the whole thing over. This frame is not connected to anything else. It is relying only on its own stiffness to keep it upright. Okay, any questions about the setup? Okay, the axial load is 400 kips. The shearing load is 6 kips, so I got 6,000 pounds trying to push this thing over. And I have a distributed load of 1.26 kips per lineal foot, which is already factored. I assume that my case of S factor for the soil stiffness is 120 psi per inch. What is required? Determine if the given column is adequate with the given loading. Solution. First step is to perform the first order analysis for this frame. The moments of inertia of the frame are reduced per ACI 318-66311 in the computer model. So in other words, when I built this frame into the computer, I used 70% of the column stiffness and I used 35% of the beam stiffness. And then I put it in the model. First, I did a first order analysis. First order analysis just means that there's no iteration. It just takes the loads you give it, runs it through the matrix stiffness method, and pumps out the resultant loading. Okay, so I could have done all this by hand. I could have used a number of methods, right, that you probably remember. The moment distribution method, the moment area method, the matrix stiffness method. There's a number of methods that you can calc out what I've done here by hand. In the interest of time and in the interest of getting to what's interesting, I just plugged it into a frame program and I let the computer find the loads for me. Okay, does that make sense to everybody?
Yeah.
Okay, so what you're looking at is just the results. Spare you all the gory details of how I created this, but this is the result. But this is the result of just the 400 kips, the 400 kips, and the 1.26 kips per foot gravity load, okay? So this is the result of all the non-lateral loads. I did not include the 6 kips that's trying to push it over, and there's a reason for that. So you run it first with just your non-lateral loads, and this is the moment diagram. So where it's fixed at the foundation, I got 15.9 kip feet. At the beam column joint, I got 31.83 and the maximum positive moment of 82.99 kip feet. Okay, so there's the moments. Here's the axial load diagram. Here's my 400 kips at each column, plus I got 17 kips from the gravity load being distributed off the beam and to the column. I got this little 1.8 kips of compression here because what's happening is there's a moment here and here, and this moment is tending to bend the columns in. It's trying to suck those columns in, and the program picks up on that. So the beam has actually got a little bit of compression holding the columns from warping in under that load. So that's where this 1.8 came from. And finally, the shear diagram. Here's the shear diagram of the gravity load on the beam. And, excuse me. And I got a little bit of shear, very little, but a little bit of shear from the beam pushing the columns out as they try to bend in. Shear from the gravity loads are opposite in direction and so cancel. So the total story shear due to gravity loads is 0. In other words, this 1.8 is in the opposite direction as this 1.8. So the net shear in this area, the story shear, is 0. Okay, now what I do is I repeat my first order analysis, but only with lateral loads. Okay, so with lateral loads, here's my moment diagram. I got 6,000 pounds that's pushing this thing over, and this is acting like a moment frame. This is a bent frame, and it's resisting that load by bending. My axial load diagram, very minimal. Basically 6 kips. 3 of the 6 kips gets transferred to this column. The first column picks up the first 3. So that's the transfer load there. And as this frame is bending over, you get some compression tension couple that's resisting a portion of the total load. And the shear diagram. And here you can see again, I've got 3 kips of shear and almost 3 kips of shear here, adding up to the total of 6 kips of lateral load. Here's my deformation from the lateral load. So this is a deformed shape, and you can see that the top has displaced by 0.214 or 0.213 inches. So that's my deformation under the factor loads. Okay, so kind of have that in your mind, the moment diagram, the axial load diagram, the shear diagram for gravity load and for lateral load, because I'm going to need those numbers to do this analysis. So the first thing we do is we test to see if this frame is really a sway frame, or are the magnitudes of the load so small that I can treat it as a non-sway frame. The test is this Q factor. So Q is equal to the sum of PU delta naught over VUS and IC, or LC, I'm sorry, where sigma PU is the sum of all factored axial loads for the story, which for this is 417 plus 417 is 834 kips. VUS is the total lateral load for the story, which for this case is 6 kips based on our loading. Delta naught is the first order relative lateral deflection due to VUS, which I found was 0.214, as you saw in that diagram. And L sub C is the height of the story measured center of joint to center of joint, 26 feet or 312 inches. So I have all my numbers. I plug them into Q, and I get a 0.095 number. What does that number mean? Well, that number is greater than 0.005, which is what the code calls out as the acceptance criteria. So 0.95 is greater than 0.5. Therefore, according to ACI, this column is a sway column. Okay, so now we know. Next, we calculate the effective length of the column. That's our K factor. So we have to find psi A at the top of the column. And I will go through this a little quicker because this is exactly the same, except to this point. Okay, so the moment of inertia of the column is 70% of 20 times 20 to the third over 12, which is 9333. BDS is the ratio of sustained shear to total shear, and that is equal to 0. None of the story shear is sustained in this case, so BDS is 0. So moment of inertia of the column is equal to the moment of inertia of the column divided by 1 minus BDS, which is still 9,333 inches to the fourth. Length of the column is 26 feet, 312 inches. And now the beam. The beam is 35% of BH cubed over 12, which is 27,216, as we've found previously. The length is 27 feet or 324 inches. And then we plug them into our psi equation as we've done before, and we get 0.356 as we did before. Psi b at the bottom of the column at the footing, it's not pinned anymore, so I got to calculate this equation with the I and K of the foundation. So this is a duplicate of what we did before. The moment of inertia of the footing is 6 times 12 times 8 times 12 to the third over 12, 5,308,000. KS is 0.120 KSI per inch. And so now I can plug it all in. 4 times moment or modulus of the column, moment of inertia of the column, length of the column over the moment of inertia of the footing times K, 0.677. So that gives me psi A, psi B. Now I can go into my interaction equation or my my charts here, but now I'm going to use unbraced frames. My alignment chart, that's the word I was looking for. So I put in the psi A, I put in psi B, and I read off the chart, and I get 1.16. Now that I have K, I got to figure out my KL over R ratio. So R is 0.3 times 20, 6 inches as before. So KL over R is 60.3. 60.3 is quite a bit larger than 22. So therefore, we have to consider our slenderness. This 22 comes from the code provision that gives you the threshold at which you can ignore slenderness. We're way above it, so we have to consider slenderness. So my Euler critical buckling load is I thought I repeated it, pi squared EI effective over KL squared, where EI effective, I'm going to use this same equation again, 0.2 EG plus ESI SE over 1 plus beta ds. But this is a different beta ds than our brace column. This is the ratio of sustained shear over total shear, which in our case is 0. I gross is 13,333. ISE, as I explained earlier, is 270. Beta ds is 0. And so my effective moment of inertia is I plug in my modulus of concrete, moment of inertia of concrete, modulus of steel, moment of inertia of the steel, beta ds is 0, and I get 17,443,000. So P sub C is now pi squared, my 17 million, 1.16 K factor, length of 312 squared. I get 1,314 kips. So then I'm going to choose to use option B to calculate delta S. So I can put in my, now remember, this is a sum of all the axial loads for that story. So I have 2 times the 417 kips. Both columns had 417 kips on them. And I have the sum of Euler's critical buckling load for all the columns. The 2 columns are identical. So I have 2 times 13, 14. And that gives me 1.73. My minimum moment is 817 kips. That should be 417 kips. Fix that one. This is lecture 13, slide 209. P is 817. Okay. Which is, yeah, this is based on, no, that was based on 800. Okay. Anyway, I'll fix this. But 81.7 either way is less than the applied moment M2. So M2, this is the part that matters. M2 is equal to the non-sway component plus delta times the sway component in that column. And it's the larger of whichever end. So these numbers come from, remember I said, remember those moment diagrams? These numbers come from those moment diagrams. 31.83 was for the gravity portion, and then the 36.81 came from the sway portion, and that gets magnified by 1.73 for a total of 95.5 kip feet. Mu over M2 is 95.5 over 31.83 plus 36.81 is the total factor. Remember, I split it into the non-sway and sway. So I add them back together and I get a ratio of 1.39. That has to be less than 1.4. So delta S 1.73 here does not need to be less than 1.4, but the total amplified moment, which we found to be 95.5, divided by the unamplified moment, which is the non-sway and sway components together, this has to be less than 1.4. And the same thing as the last one. If it's not, you got to fix it. You got to get it so that it's less than 1.4. 1.39, we just squeaked by. I can use the same column interaction diagram as I did from example 3 because it's the same actual frame. So the section properties didn't change. So all of this is exactly the same as what we did from example 3. Onto this, we can plot our load, which was 95.5 kip feet and 417 kips of axial load. And that goes right there. So since the magnified load still fits within the interaction diagram, then this design is acceptable. And the total amplified moment was 1.39 of the original moment. So that criteria was met. This criteria is met. We got a good design. That column will work. In the real world design, all load cases would need to be evaluated. So this is how I would do it with software. This is SP column again. Here's that column with the 8 number 7s, 4 on each side. And there's those load cases. I plotted them in there for you. So this is what it would look like in a real world design. Okay. Any questions?
So, Professor, it's still acceptable even though the delta is 1.73?
It is. It is. For the sway column, they're not looking at the amplification of the sway portion, because what if the sway portion is really, really small? Then who cares if it's 10 times something that's really small? So no, they have no limit on delta S. But what they say is when it's all said and done, what the total original moment was, the amplified moment can't be more than 1.4 times the total original moment. So they put the restriction looking at the total, not just the delta sway part.
Okay, and then I have a question about the factored actual load.
Mm-hmm.
Why is it 417 only?
Because we're looking at one column.
Yeah, but what I mean is when you factored 400, what did you times it by?
No, the 400 was already factored. Here, let me show. I'll show you.
Okay.
Going way back. Didn't update. Okay, bear with me a sec. Figure this out. Still didn't want to do it. Ah, you stink. Does anybody love Microsoft? Like anybody? Where was that? Right there. There we go. Okay, that's what I was trying to get to. So PU is 400 kips. So you have 400 kips coming down on this column, 400 kips coming down on this column. And it's P sub U. So the work of factoring, the 1.2, the 1.6, that's already been done. It's already factored. But why is it 417? It's 417 because we have this W distributed load here that is being also carried by the two columns. So when I analyzed that in my frame program, what I got was 417 and 417. But these are already factored.
Oh, okay. I forgot that uniform load over there.
Yeah, okay. So yeah, the uniform load is going to the ends of the beams and shear, but then it becomes a compression being supported by the columns.
Right. Okay. Thank you.
Sure. Okay, so we basically have a whole nother hour, and this is all I prepared for tonight. So I've got all kinds of time to answer any questions you may have. Oodles of time.
Wait, that's it for our lecture?
Yeah. Yeah, I wrote it because usually the one we did last time usually goes long. So it usually carries over to this night. And then when I add this one to it, it gets me a lot closer to 7 o'clock. But we just whistled right through it last time. So this is it. So either you have lots of opportunities to ask those burning questions that you never had an answer to, or we call it a night and we all go eat dinner and watch Netflix. Starting to look like Netflix. Anybody?
I mean, I have a question, but it's from homework 6.
That's fine.
Okay. Can you go to the solution for homework 6?
Sure.
And number 4.
Uh-huh.
So when you were asking about the maximum spacing anywhere on the span, is it
Mhm.
like in your example you use for the case number 4, which is just the d over 2? Is that always the case?
Okay, so remember the lecture that we did for shear ties, and we
Mhm.
had like 5 different things you have to check.
Right.
But it depended on whether or not VS is greater or less than 4 square root f prime c b d. And so if it's greater than that, your maximums are d over 4 or 12 inches. But if it's less than that, then it's d over 2 or 24 inches. Okay, so we did this check here and we found that the 4 square root is greater than Vs. So
Mm-hmm.
therefore, my maximum spacing anywhere is d over 2 or 24 inches, whichever of these two is less. But we also have to check this dog, which is the AVFY over 50B as a maximum spacing. So it's either this or whatever you need because of the demand on the concrete.
Oh, so since the VS required is less than the 4 square root of FCBWD, we have another two options, right? Which is
Yes,
the
yes,
over 2 or 24 inches.
right.
Ah,
But
okay.
if your VS was greater than 4 square root, then it becomes D over 4 or 12 inches. It gets tighter if you have a more highly stressed beam.
Oh, so there's two options for now. Okay. And then, okay. And then for number one, I just want to clarify that you do not factor the loads for this one.
Correct. Yeah, we're dealing with the cracked moment of inertia, the cracking moment. Uh, what did I ask for? I asked for stress. So yeah, those are not factored. Okay, and that's problem number 2. But yeah, these are serviceability questions. So correct, you do not factor them.
But I think in your uh example, you factored it out.
No way.
Oh, I mean, I can check that out later. And then I just want to clarify because I remember it vaguely that there's one point that we don't need to factor the load. And I just want, and then I saw this one and you didn't factor it because I got this solution last time and then I changed it because I thought I forgot to factor it out and I was wrong. Okay.
Okay, well there's an easier way to think about it, I think.
Mm-hmm.
If you are checking the flexural capacity. So remember the end game, the ultimate goal of checking flexural capacity is to get to a point where you can say phi mn is greater than mu.
Mm-hmm.
Well, that u tells you that you have to factor those moments. Same thing with shear. If you're checking shear capacity, the end game, you're not done until you show me that phi mn is greater than vu. Well, there's a u in there. That tells you you have to use factored loads. For the column designs that we just started working through, the end game is for you to tell me that phi pn is greater than pu. The u, again, tells you it has to be factored loads. But when we're talking about deflections, if we're talking about the load it takes to cause cracking, or checking a crack width, or checking these service stresses, F sub C and F sub S, well, these are all based on the flexural equation. That stress is equal to my over I. My over I is only applicable in the elastic range of a material. And factor loads are never in the elastic range of elastic or materials. So all of this that you see here, I cracking, M cracked, finding the short-term deflection, finding long-term deflection, telling me what the stresses are with FC and F sub S, these are all based on service loads.
Mm-hmm. Oh, so you don't need to factor it
You do not,
technically.
no, well, it's not that you don't need to, it's that it's wrong if you do.
Okay.
By definition, service load checks are with service loads. Service loads have no factors on them.
Right. Okay. And okay, lastly, go back to home number 4 again.
Uh-huh.
So when you're asking for the region with no ties needed,
Yes.
and that one starts from the middle to certain X, right?
Yes.
Which is you put it with the 1/2 PVC,
Yes.
and you didn't show what is the value of your X. Oh, here it's 3.05. It's
3.05. Yeah.
it's in the last thing.
Yeah.
And so it's always like this, right? If you want to find the ones with no shear ties at all, you always need to go to 1/2 PVC.
Correct. Yes. And then, because you're going from the point of zero shear, which for a uniformly loaded beam is at midspan. So I'm going from midspan out to the point using similar triangles to the point where I have too much shear to not have any ties. So it's only from this threshold to the point of zero shear in the middle that I can not provide ties. And then of course it's a mirror image. You have the same region on the other
On
side
the other side, yeah.
of the 0 point. And oh, okay. And then what I did was I found out as a maximum how big that space can be, 3.05 feet. Then what I did is I took the whole half of the span minus that to give me that I have to have ties for at least 10.95 feet. I have to cover 10.95 feet. So I will put enough ties in there to go at least that far and maybe a little bit more, but not less than the 10.95.
Oh, okay. Because
Okay.
I stopped when I found the non-region, and then I kept I got 9.67 feet that has needed a shear tie. I guess that one is wrong.
Yeah, I found that I need ties for 10.95 feet as a minimum, and you have to go more than, you can't go less than. If you go
Oh,
less than, then you're going to stop your tie right over here someplace, and you'll have this region that violates code because you'll have too much shear to not have any ties.
yeah, you're technically missing like some ties, right?
Right. Yes.
Okay.
Yeah. Now I can say in common practice in the real world, we don't we don't do this. It's just not worth it. So whatever we'll step down, you need a lot of ties at the end, and then you could use half as many ties in the middle region, and we'll use the middle region with less ties, but we won't go to a point of no ties. We don't do that. It's just
Mm.
not worth it. So we'll put a lesser region in the middle and a more tightly spaced region at the end.
Okay, that makes sense. And I think that's it, Professor, for the homework.
Okay. All right. Before I close it up, does anybody else have any questions they would like to ask? All right. Use your extra hour, well, 45 minutes. Use the extra 45 minutes of your life wisely and smartly, and have a great weekend. We'll see you next week.
Thank you, Professor.
Thank you.
Much appreciated. See ya. Have a restful evening.
Thank you. You too.